So we're going to talk about a couple of different things. So we're going to talk about continuity. So typically the graphs we've worked with so far have been a nice continuous curve, very few breaks, holes, and gaps in it. I threw in a couple throughout these last couple sections where it does split up into a couple different pieces. So when we have that, it just means it's a non-continuous function. So a continuous function just means there's no breaks, holes, or gaps in your function. Like I said, for the most part, those are the values, or those are the graphs we've been looking at. So we haven't really had to worry about this. But like I said, every once in a while, I'll throw in a couple of a couple of graphs that are split up. So like I know there's one assignment that had a graph that had like two different pieces going on. There was one that was a straight line, and then there's a little jump. So there's been a couple of those graphs that I've been working into your assignments to kind of get you familiar with those before we officially talk about it. Okay. So those continuous functions are the ones we've been working with. We just haven't necessarily had to call them continuous because we've had only continuous functions. So the graphs that are not continuous have limits. So they have values that they're approaching but never quite crossing. So usually when in math we're going to say approaching instead of writing out the whole word, we use an arrow. So if you ever see a little arrow pointing to a number, that means it's approaching that value. It's never quite crossing that. So that is a limit for our graph. The other thing we talk about is if it's a value that's approached but never crossed throughout the entire graph, we call that something called an asymptote. So usually if you see a graph that's kind of starting to level at a value, so it comes up and it basically hits a wall, and then it kind of starts going straight right at that value. That's called an asymptote because it's a value that's approached but never quite crossed. So when you look at graphs, like I said, that kind of hit a wall but still turn, it's hitting an asymptote. Is what it's hitting. So we're going to look at three different types of discontinuity. This is one probably most often we'll look at. It's infinite discontinuity. That means that there's one value that the graph just comes up really, really close to, but never crosses. So this would be like an asymptote, this value. So this side of the graph is going along, and it basically hits a wall, but then it still goes straight down, okay? So it doesn't just stop there. It just kind of hits that and just kind of follows that asymptote for the rest of the time. Same thing on this side. It's going along, and it basically hits a wall, but it doesn't stop. It just starts shooting up instead. So that would be that asymptote kind of in the middle of that graph. And there's actually one here too. So notice they're both going kind of off in all different kinds of directions. But this graph, there is a couple of values that it just will never reach. So that's why it's broken up into two different pieces. So it kind of hits that asymptote, hits that wall, and kind of shoots it up or shoots it down. And that's infinite discontinuity. So the graph is still technically going on in all directions. So it's still going left, and still going right, still going up, still going down. But it's kind of in pieces because of that wall that it hits. They can't cross it. This one is jump discontinuity. So the graph is in a couple of different pieces. This is on the next page. We don't see these as often because in order to create something like this, you have to specifically write it that way. With the infinite discontinuity, it could just look like a regular equation. It just, when you graph it, it kind of breaks up into pieces like that because of some discontinuity. Jump discontinuity just basically puts different pieces of graphs, and so there's this big jump kind of. So your graphs go along, and all of a sudden hits this value, and then it jumps up and starts again. So it doesn't really hit a wall. There's a part of the graph, it hits a value, then it jumps, keeps going, and you can actually do it a couple of different times. So that is jump discontinuity. So there's that kind of jump in between those values. And then the other one that we see a little more often than jump discontinuity is removable discontinuity, and this one's harder to see because it looks like it's a nice continuous curve, but there's actually a hole in it. Okay, so like this one, it looks like a line, but there's actually a gap right there, a value that it can't reach. Okay, and usually when we have something like that, your equations look like this, where there's some division in there. And so the reason why there could be a hole there is if you're dividing, you can't divide by 0. And so, like with this one, if I make x negative 4, that would make the bottom 0. And so we can't divide by 0, so it just kind of has to skip over that value because we can't divide by 0. So that's why some graphs can just have a random hole in it because of that divide by 0 hole. So that's kind of the 3 different discontinuities that we can have. So the big thing we're going to do is, for the most part with this, we are giving you an equation and we're going to check if it's continuous at a point. So we're going to do the continuity test. In order to check the continuity test, basically you are given a function and you're either given one value or two values or multiple values to check, okay? And so the things that are continuous outweigh the things that are not. So really, the two big no-nos that we look for that to not be continuous is if you have to divide by 0, because we know we can't do that, and also square rooting a negative. So I know that we talked about in complex numbers that we could change that to i's, but again, technically we're entering into an imaginary unit. We want to stay in real numbers with functions. So the two big no-nos you check for are, am I having to divide by 0? If I have to divide by 0, that's not continuous. If I have to take the square root of negative, it's also not continuous. So those are the only two things that make something not continuous. So what we're going to do, to determine if a function is continuous, I'm going to give you some sort of function, and then actually I've given you a couple values we're going to check. We're going to check negative 4 and positive 4. So we're going to do two separate checks. So what we need to do with those values, we're going to plug in those numbers, like I said, separately, because we're going to check two different things. I'm going to put negative 4 into my function and check it. So since this one's a square root, if I get a square root of something that's not negative, then we're going to say that's continuous. If we get a square root that is negative, we're going to say it's not continuous. So those are our two options. So I'm going to take negative 4 and plug it in first. So I'm going to check that value. Everyone with me so far? So, like I said, we have two values we're going to check. So I'm checking negative 4 first. So I multiply that out. So I got negative 2 times negative 4 is negative 8. Negative 8 minus 3 is negative 11. So I have the square root of negative 11. So I have to look, am I dividing by 0? I don't need to worry about that. Do I have the square root of a negative? Am I square rooting a negative? Yep. So then we'd say this is not continuous. And then sometimes I like ask for a reason. So it's over square root of a negative. So if we look at that graph, there's not going to be a value there because you have the square root of negative. So square root of a negative, like I said, switches it to I. We could do that, but like I said, if we look at the graph of that, you're not going to find a value of the function there, okay? Because you have the square root of negative, and you can't mix real numbers and imaginary numbers on function graphs. Questions about the first value? So we did 4, or negative 4. Now we're going to check positive 4. So we're going to take 2 times 4, which is 8. And subtract 3, we get 5. So with positive 4, are we square rooting a negative? No. So we say that this is continuous. So as long as we get a square root that's not negative, it is continuous. If we get a square root that is negative, it's not continuous. Questions about that example? Like I said, when we're doing the continuity test, we're really looking for two things. Are we having to divide by 0 or square root of negative? Those two things make it not continuous. Everything else is continuous. tell which one you're looking for. So if you have a square root, you're going to look for, am I having to square a negative? If I have a big fraction like this one I'm going to have to worry about dividing by 0. So again, I'm going to check two values to see if either one of these are continuous. Again, everything's continuous except for if you have to divide by 0 or square root a negative. So I'm going to try 2 first. Make sure you plug it in for both x's. So I'm going to have 2 separate answers. So I'm going to put 2 in first. And so then I'm going to solve this one out. So on the top I'll have 2 squared is 4. And 4 minus 4 gets 0. Okay? 0 on the top is fine. Okay? So I haven't seen anything that's not continuous yet. But if I solve out the bottom, what do I get down here? I take 2 minus 2. 0. Okay? So, like I said, the 0 on top really doesn't matter. It's if I get a 0 on the bottom. Because that means I'm dividing by 0. Can I divide by 0? No. So this would be not continuous. You're dividing by 0. So I've checked 2. Now I'm going to check negative 2, see if that works. So on the top, I plug it in, I get negative 2 squared, which is 4. And then on top is 4 minus 4 is 0. Okay, again, I've got 0 on the top again. But like I said, that's not the 0 that makes it not continuous. It's if it's 0 on the bottom. Am I going to get 0 on the bottom?
No.
No. So negative 2 minus 4 is negative 6. Okay? So this one's okay. This one's just going to be 0. Because 0 divided by anything is 0. So I can actually get a value. So this one is continuous. Okay? Because I didn't divide by 0, I divided by negative 6. And you can divide by negative 6 with any number that you want.
How do you get negative 6?
Because negative 2 minus 2. Good question. I wrote the wrong number. That's why I got negative 6.
Okay. I thought I did something wrong.
No, it's again Monday. Divided by negative 4.
It's a Monday.
It's a Monday.
You're okay.
Thank you. So again, we can divide by negative 4 with anything. So 0 divided by negative 4, 0. Sorry about that. Questions about this one? Helps me write down the right number. Okay. So that's the continuity test. So the next thing we're going to talk about is something called end behavior. And this is kind of related to domain and range, but not really. Mostly it's, there's a lot of notation with this one. So basically what you're going to look at is what the ends of the graph are doing. So the very left end and the very right end. So we're always going to be able to look left and right. And so you're going to answer what it's doing up and down. So if I look to the left and it's going up forever, we're going to say it's positive infinity. If I look to the left and it's going down forever, it's negative infinity. Or sometimes you have graphs that level out at a number. And so if you're looking left and it's like one of those graphs that's shooting off left forever, then we're going to say whatever number that is. So those are our 3 options when we're doing end behavior. So it's either going up forever, which is positive infinity, down forever, negative infinity, or it's leveling out, so it's going to be a number. So like I said, there's a little bit of notation. So to say something's going left, we're going to say x, and we're going to use that new symbol I wrote on the first slide, is approaching, okay? So whenever you see that arrow is approaching negative infinity, that means we're saying we're looking to the left of the graph. So we're not going to have to write left. So what you'll have to do for me for the notation is write x is approaching negative infinity. And like I said, if you write it like this, then I know that you're talking about the left end. So on this first example, I'm going to write it out in words, but for the most part, you won't, like I said, you won't have to write left end. because if you write x is approaching negative infinity, that tells me that we're looking at the left end of the graph. Okay? So then what we're going to answer is what f of x is doing. So like I said, in paper has a little bit of notation. So like I said, you're not going to write the words every single time, but this is what we're looking at. So we're looking at the left end of the graph, which is right here. And like I said, usually if there's no dots, assume there's an arrow. So we have a left end and a right end. So right now I'm looking at the left end. So I have to answer, is it going up forever, down forever, or is it leveling out? So look at the left end. What's it doing? Is it going up, down, or leveling out?
Down.
It's going down. So if we look at the left end and it's pointing down like this forever, then we're going to say that f of x is approaching negative infinity since it's going down. So this is telling me that the left end is going down by using that notation. So left end going down. So x approaching negative infinity is telling you left end. F of x approaching negative infinity is telling you it's going down. Okay, so now we're also going to do the right end because each graph has two ends, a left end and a right end. So left end, x is approaching negative infinity. Right end, x is just approaching infinity because we're going off to the right. So yeah, we're saying what the graph is doing. So we're saying what the function is doing. So that's why it's f of x. So if we look at the left end, is it going up, down, or leveling out?
Up.
Up. So if it's going up, we're going to say it's positive infinity. So like I said, I wrote the words this time so you can get used to the symbols. So by saying x is approaching negative infinity, f of x is approaching negative infinity, you're saying the left end is going down. If you're saying x is approaching positive infinity and f of x is approaching positive infinity, you're saying the right end is going up. Questions? Like I said, it's a little weird because of the notation. So that's why I tried to write the words with it. So the next example, I'm not going to write the words, I'm just going to use the symbols. These do not have to be the same. So like right now, both of them were negative infinity for the left end. Both of them are positive infinity. They don't have to be the same. You could have your function could be on both ends going up, so they both could be positive infinities. They both could be going down, so your ends could both be negative infinities. Like I said, they could be leveling out at a number. And we're going to look at a graph like that so you know what I'm talking about with that. So again, they don't have to be one of each for your function. These are going to be the same each time, but you're always going to look to the left end and the right end. So you're always going to have x approaching negative infinity and x approaching positive infinity. F of x will change. Like I said, you might have one of each. So like one might be going down, one might be going up. They both might be going down. They both might be going up. Or like I said, they could be leveling out. So this depends on what the answer is. We're looking at the left end, so we're looking at the left side of the graph. So that's why when you see x approaching negative infinity, we're talking about the left end, which our left end's over here. So is our left end going up, down, or leveling out? It's going up. So we're going to say f of x is approaching positive. So again, when I read that, it's x is approaching negative infinity, so left end, f of x is approaching positive infinity, it's going up. Now I'm going to look for the right end. What's the right end doing? It's also going up. So we're going to say f of x is approaching positive. So like I said, you always have x will be the same each time. So you'll always have one x that's approaching negative infinity, one x that's approaching positive infinity, because again, we're always looking to the left and the right side of the graph. our function will change. Like I said, our last one, they had one of each. One was going down, one was going up. So we had a negative infinity and positive infinity. This graph, both ends are going up, so both of them are positive infinity. Or we might have graphs like this. So like I said, now that we know a little bit more about discontinuity, we can have graphs that have different pieces. But we can also do in behavior. I know this is kind of weird, but like I said, eventually what could happen is right now we're looking at a graph and I'm giving you all the parts, but I could give you all the parts and then you can sketch a graph is what this is leading to. So that's what helps with the behavior. So with this one, like I said, notice I went ahead and wrote some of the notation already. So like I said, this is going to be similar each time because you're always going to look to the left end, the right end. Really what's changing is what f of x is approaching. So with this one, I know there's a ton of arrows, but what we have to do is these middle arrows are not the ends, okay? They're kind of in the middle. So what we're doing is looking at the very left end and the very right end. So that's why you have to make sure you're careful. We're looking at the very left end and the very right end. So we're not worried about these middle ends, okay? Because these are in the middle, so they're not as far left or right as the graph goes. So we're looking at the very left. So if you look at this arrow, is it going up forever, down forever, or is it leveling out?
Can level out.
This one's leveling out. Okay, so like I said, if it's going up forever, you have to really make sure it's going off in the distance. Down, same thing. This one is one that's going to level out. Okay, and so when it levels out, we're going to say roughly what number it's leveling out at. And so we look at that y value. What do you want to say?
1.
1. Yep. So this one's leveling out at 1. So like I said, the end behavior doesn't have to be infinities. It could be a number. So if you have a graph like this, it's going to level out. So now we're going to look at the very right end. The very right end is over here. Is it going up forever? Down forever? Or is it leveling out? Is it going up, down, or leveling? Leveling out. Okay. And what value do you want to say for that? 1. Yep. Most of the time they're leveling out at the same value. So not always. Okay, they don't always have to level out the same value, but a lot of times they do. There is in behavior. Any questions? No executed today. Just a worksheet. And it's just front and back. So the front page you're doing the continuity test. The back page you're doing in behavior. So a little bit of each.